Contact mechanics is the study of the deformation of solids that touch each other at one or more points. The physical and mathematical formulation of the subject is built upon the mechanics of materials and continuum mechanics and focuses on computations involving elastic, viscoelastic, and plastic bodies in static or dynamic contact. Central aspects in contact mechanics are the pressures and adhesion acting perpendicular to the contacting body's surfaces and the frictional stresses acting tangentially between the surfaces. This page focuses mainly on the normal direction, i.e., on frictionless contact mechanics. Frictional contact mechanics is discussed separately. Contact mechanics is part of mechanical engineering. It provides necessary information for the safe and energy-efficient design of technical systems, and for the study of tribology and indentation hardness. Principles of contact mechanics can be applied in areas such as locomotive wheel-rail contact, coupling devices, braking systems, tires, bearings, combustion engines, mechanical linkages, gasket seals, metalworking, metal forming, ultrasonic welding, electrical contacts, and many others. Current challenges faced in the field may include stress analysis of contact and coupling members and the influence of lubrication and material design on friction and wear. Applications of contact mechanics further extend into the micro and nanotechnological realm. The original work in contact mechanics dates back to 1882 with the publication of the paper on the contact of elastic solids by Heinrich Hertz. Hertz was attempting to understand how the optical properties of multiple, stacked lenses might change with the force holding them together. Hertzian contact stress refers to the localized stresses that develop as two curved surfaces come in contact and deform slightly under the imposed loads. This amount of deformation is dependent on the modulus of elasticity of the material in contact. It gives the contact stress as a function of the normal contact force, the radii of curvature of both bodies and the modulus of elasticity of both bodies. Hertzian contact stress forms the foundation for the equations for load-bearing capabilities and fatigue life in bearings, gears, and any other bodies where two surfaces are in contact. History. Classical contact mechanics is most notably associated with Heinrich Hertz. In 1882, Hertz solved the contact problem of two elastic bodies with curved surfaces. This still relevant classical solution provides a foundation for modern problems in contact mechanics. For example, in mechanical engineering and tribology, Hertzian contact stress is a description of the stress within mating parts. The Hertzian contact stress usually refers to the stress close to the area of contact between two spheres of different radii. It was not until nearly 100 years later that Johnson, Kendall, and Roberts found a similar solution for the case of adhesive contact. This theory was rejected by Boris de Jayon and co-workers who proposed a different theory of adhesion in the 1970s. The de Jayon model came to be known as the DMT model, and the Johnson al. model came to be known as the JKR model for adhesive elastic contact. This rejection proved to be instrumental in the development of the Tabor and later Maugis parameters that quantify which contact model represent adhesive contact better for specific materials. Further advancement in the field of contact mechanics in the mid-20th century may be attributed to names such as Bowden and Tabor. Bowden and Tabor were the first to emphasize the importance of surface roughness for bodies in contact. Through investigation of the surface roughness, the true contact area between friction partners is found to be less than the apparent contact area. Such understanding also drastically changed the direction of undertakings in tribology. The works of Bowden and Tabor yielded several theories in contact mechanics of rough surfaces. The contributions of Archard must also be mentioned in discussion of pioneering works in this field. Archard concluded that, even for rough elastic surfaces, the contact area is approximately proportional to the normal force. Further important insights along these lines were provided by Greenwood and Williamson, Bush, and Persson. The main findings of these works were that the true contact surface in rough materials is generally proportional to the normal force, while the parameters of individual microcontacts are only weakly dependent upon their load. Classical solutions for non-adhesive elastic contact. The theory of contact between elastic bodies can be used to find contact areas and indentation depths for simple geometries. Some commonly used solutions are listed below. The theory used to compute these solutions is discussed later in the article. Contact between a sphere and a half-space. An elastic sphere of radius indents an elastic half-space to depth, and thus creates a contact area of radius. The applied force is related to the displacement by wear and are the elastic moduli n, the Poisson's ratios associated with each body. The distribution of normal pressure in the contact area as a function of distance from the center of the circle is where is the maximum contact pressure given by the radius of the circle is related to the applied load by the equation. The depth of indentation is related to the maximum contact pressure by the maximum shear stress occurs in the interior at for contact between two spheres. For contact between two spheres of radii and the area of contact is a circle of radius. The equations are the same as for a sphere in contact with a half plane, except that the effective radius is defined as contact between two crossed cylinders of equal radius. This is equivalent to contact between a sphere of radius and a plane. Contact between a rigid cylinder with flat-ended and an elastic half-space. If a rigid cylinder is pressed into an elastic half-space, it creates a pressure distribution described by where is the radius of the cylinder and the relationship between the indentation depth and the normal force is given by contact between a rigid conical indenter and an elastic half-space. In the case of indentation of an elastic half-space of Young's modulus using a rigid conical indenter, the depth of the contact region and contact radius are related by with defined as the angle between the plane and the side surface of the cone. The total indentation depth is given by the total force as the pressure distribution is given by the stress has a logarithmic singularity at the tip of the cone. Contact between two cylinders with parallel axes. In contact between two cylinders with parallel axes, the force is linearly proportional to the indentation depth. The radii of curvature entirely absent from this relationship. The contact radius is described through the usual relationship with as in contact between two spheres. The maximum pressure is equal to bearing contact. The contact in the case of bearings is often a contact between a convex surface and a concave surface. The method of dimensionality reduction. Some contact problems can be solved with the method of dimensionality reduction. In this method, the initial three-dimensional system is replaced with the contact of a body with a linear elastic or viscoelastic foundation. The properties of one-dimensional systems coincide hereby exactly with those of the original three-dimensional system. If the form of the bodies is modified and the elements of the foundation are defined according to the rules of the MDR. However, for exact analytical results, it is required that the contact problem is axisymmetric and the contacts are compact. Hertzian theory of non-adhesive elastic contact. The classical theory of contact focused primarily on non-adhesive contact where no tension force is allowed to occur within the contact area, i.e., contacting bodies can be separated without adhesion forces. Several analytical and numerical approaches have been used to solve contact problems that satisfy the no-adhesion condition. Complex forces and moments are transmitted between the bodies where they touch, so problems in contact mechanics can become quite sophisticated. In addition, the contact stresses are usually a nonlinear function of the deformation. To simplify the solution procedure, a frame of reference is usually defined in which the objects are static. They interact through surface tractions at their interface. As an example, consider two objects which meet at some surface in the plane with the axis assumed normal to the surface. One of the bodies will experience a normally directed pressure distribution and in-plane surface traction distributions and over the region. In terms of a Newtonian force balance, the forces must be equal and opposite to the forces established in the other body. The moments corresponding to these forces are also required to cancel between bodies so that they are kinematically immobile. Assumptions in Hertzian theory. The following assumptions are made in determining the solutions of Hertzian contact problems. The strains are small and within the elastic limit. The surfaces are continuous and non-conforming. Each body can be considered an elastic half-space. The surfaces are frictionless. Additional complications arise when some or all these assumptions are violated, and such contact problems are usually called non-Hertzian. Analytical solution techniques. Analytical solution methods for non-adhesive contact problem can be classified into two types based on the geometry of the area of contact. A conforming contact is one in which the two bodies touch at multiple points before any deformation takes place. A non-conforming contact is one in which the shapes of the bodies are dissimilar enough that, under zero load, they only touch at a point. In the non-conforming case, the contact area is small compared to the sizes of the objects and the stresses are highly concentrated in this area. Such a contact is called concentrated, otherwise it is called diversified. A common approach in linear elasticity is to superpose a number of solutions, each of which corresponds to a point load acting over the area of contact. For example, in the case of loading of a half-plane, the Flamant solution is often used as a starting point and then generalized to various shapes of the area of contact. The force and moment balances between the two bodies in contact act as additional constraints to the solution. Point contact on a half-plane. A starting point for solving contact problems is to understand the effect of a point load applied to an isotropic, homogeneous, and linear elastic half-plane, shown in the figure to the right. The problem may be either plane stress or plane strain. This is a boundary value problem of linear elasticity subject to the traction boundary conditions. Whereas the Dirac delta function, the boundary conditions state that there are no shear stresses on the surface and a singular normal force P is applied it. Applying these conditions to the governing equations of elasticity produces the result for some point in the half-plane. The circle shown in the figure indicates a surface on which the maximum shear stress is constant. From this stress field, the strain components and thus the displacements of all material points may be determined. Line contact on a half-plane. Normal loading over a region. Suppose, rather than a point load, a distributed load is applied to the surface instead, over the range. The principle of linear superposition can be applied to determine the resulting stress field as the solution to the integral equations. Shear loading over a region. The same principle applies for loading on the surface in the plane of the surface. These kinds of tractions would tend to arise as a result of friction. The solution is similar to the above but altered slightly. These results may themselves be superposed onto those given above for normal loading to deal with more complex loads. Point contact on a half-space. Analogously to the Flamant solution for the 2D half-plane, fundamental solutions are known for the linearly elastic 3D half-space as well. These were found by Boussinesq for a concentrated normal load and by Cerruti for a tangential load. See the section on this in linear elasticity. Numerical solution techniques. Distinctions between conforming and non-conforming contact do not have to be made when numerical solution schemes are employed to solve contact problems. These methods do not rely on further assumptions within the solution process since they base solely on the general formulation of the underlying equations. Besides the standard equations describing the deformation and motion of bodies, two additional inequalities can be formulated. The first simply restricts the motion and deformation of the bodies by the assumption that no penetration can occur. Hence the gap between two bodies can only be positive or zero where denotes contact. The second assumption in contact mechanics is related to the fact that no tension force is allowed to occur within the contact area. This leads to an inequality which the stresses have to obey at the contact interface. It is formulated for the contact pressure since for contact, the contact pressure is always negative, and further for non-contact the gap is open, and the contact pressure is zero. The so-called Kuhn-Tucker form of the contact constraints can be written as these conditions are valid in a general way. The mathematical formulation of the gap depends upon the kinematics of the underlying theory of the solid, non-adhesive contact between rough surfaces. When two bodies with rough surfaces are pressed into each other, the true contact area is much smaller than the apparent contact area. In contact between a random rough surface and an elastic half space, the true contact area is related to the normal force by with equal to the root mean square of the surface slope, and the median pressure in the true contact surface can be reasonably estimated as half of the effective elastic modulus multiplied with the root mean square of the surface slope. For the situation where the asperities on the two surfaces have a Gaussian height distribution and the peaks can be assumed to be spherical, the average contact pressure is sufficient to cause yield when whereas the uniaxial yield stress and is the indentation hardness. Greenwood and Williamson defined a dimensionless parameter called the Plasticity Index that could be used to determine whether contact would be elastic or plastic. The Greenwood-Williamson model requires knowledge of two statistically dependent quantities, the standard deviation of the surface roughness and the curvature of the asperity peaks. An alternative definition of the plasticity index has been given by Mikic. Yield occurs when the pressure is greater than the uniaxial yield stress. Since the yield stress is proportional to the indentation hardness, MICIC defined the plasticity index for elastic-plastic contact to be in this definition represents the micro-roughness in a state of complete plasticity and only one statistical quantity. The RMS slope is needed which can be calculated from surface measurements. 4. The surface behaves elastically during contact. In both the Greenwood-Williamson and Mikic models the load is assumed to be proportional to the deformed area. Hence, whether the system behaves plastically or elastically is independent of the applied normal force.